The next part will be, I guess, yeah, no new faces. The next part will be on the L2 guarantee, achieving the L2 guarantee in a stream. So you guys remember the L2 guarantee, that you want items whose squared frequency is at least phi times f2, where f2 is the sum of squared frequencies. And we noticed in some cases that can be a much stronger guarantee than the L1 guarantee. Okay, so let me show you how you can achieve the L2 guarantee. It's a data structure called CountSketch, due to Charikar, Chen, and Frack Colton. And it does the following. So you assign each item, or sometimes I'll call the coordinate I, a random sign sigma I. Okay, with probability 1/2 it's 1, with probability 1/2 it's -1. And what you're going to do is you're going to randomly partition the items into B hash buckets, okay, using a hash function, similar to what we saw in the last part. The difference is, inside of a hash bucket, you're not just going to maintain the sum of the frequencies that go there. You're going to maintain the signed sum. Okay, so in the jth bucket, you have a counter C sub j, and it's the sum over all items I for which the hash function of I equals j, they go to the jth bucket, of the sign sigma I times the frequency fi. Okay, so pictorially, you have this vector of items. These are their frequencies, and they hash to buckets. For instance, the second item hashes to the second bucket, and in there I'm maintaining this signed sum. Okay. Note that this is very easy to maintain in a stream, because if I get an update to an item, say I get an insertion to item 2, then I just added sign to the corresponding bucket. And at the end of the stream, I'll have maintained this count. So this is a good data structure for estimating individual frequencies. So how can I estimate frequency f sub I? So what I do is I look at the hash bucket it goes to, h of I. There's some count there, c of h of I. And I multiply it by its sign, sigma I. Right? Every item is associated with a sign. So I claim this is an unbiased estimator. Do you see why? Because, suppose this item goes to this bucket here. Then the sigma i's are going to cancel. Sigma I squared is equal to 1, right? Because it's a sign. So I'll multiply by sigma I, and I'll get sigma I squared times fi. I'll get fi, plus everything else in the bucket. That'll have the form sigma I times sigma j times f sub j. But the expectation of sigma I, sigma j is 0 for two distinct items, I and j. Right? Because they're random independent signs. Is it clear?
It's true in an ensemble sense, but for any one draw, you're certainly going to have somebody who's correlating with you, right?
No, so for the moment, let's assume all these signs are independent. Okay, so like what is happening inside of a bucket, right? Like I have, sum of j such that h of j equals h of I. I have sigma I times sigma j fj. This is what's inside of the bucket that I goes to, and I said my estimator is sigma I times the count. Yeah? And if I look at the expectation of this, yeah, I get sigma I squared fi. This is deterministically equal to fi. Plus, by linearity of expectations, sum j such that hj equals hi, expected value of sigma I, sigma j, fj. Yeah? And this is 0 for I does not equal j, because we already took out the I. This is 0 always. So it's an unbiased estimator. Yeah. Still some confusion? This is 0 because, sorry, you look confused. No? It's OK? Yeah, so right? Because I mean, with probability 1/2, this is 1. Probability 1/2, it's -1. So this is 0. OK.
Coordinates in this case are locations in the stream, right?
No, I'm sorry. Maybe that was the confusion. So the coordinates are the items.
Okay, they're items.
Yeah. So think about a vector corresponding to all the items. OK, the ith position is the ith item. And the vector, the value in the ith coordinate, is the frequency of item I. OK, so I have this vector of length n, and the value in the ith position is frequency I. OK, and we know the sum of all the frequencies is the stream length.
Yeah, so then my point is that it's not ergodic. Yeah, the ensemble average is uncorrelated, right? But if you actually pick the thing, if somebody else big lands there, you don't get any kind of time average to get rid of them, right? Like if two items have the same size,
Yeah.
then they're.
Oh yeah, but I'm just saying an expectation.
But it's like there's a time expectations that ergodic.
Oh, just think about at the end. Just think about at the end of the stream. This is you estimate the frequency at the end of the stream. Okay, so there's no notion
Of multiple time. And I'm also not sure I understand the question. Like,
I think the question that he's trying to get
Yeah.
is, imagine you are preserving this guarantee at all points of time. That's a slightly different question. So the way to think of it is you run your algorithm, and then I say comment, and you give the answer 1. What you're raising is, given that I have answered in a time 10, that answer is definitely correlated with the answer at time 10.
yeah, that's definitely true.
That's not being addressed here.
Yeah. So think about this as just estimating the frequency after processing the stream. There's just one time step. OK. OK, so that's the expectation. OK, so suppose we repeat this basic hashing scheme independently. Yeah.
For two items, if they are in the same bucket and the same sign, they have the same expectation, right?
So the expectation is over the sign. So I don't know what. I mean, it's all. Yeah.
Doesn't work at all if you use it once. You have to use it independently many times, right?
Yeah.
I think that's
Oh no. I mean, if you just want one estimate, you just do it once and you compute this. Its expectation over the signs is going to be the frequency.
Yeah, but its probability of being totally wrong is high.
Oh yeah, there's a variance and all that. Yeah, I'm gonna. Yeah. No, I said unbiased estimator, right? So okay, yeah.
So it only makes sense if you repeat the whole thing.
Yeah. That's what we're gonna do to get concentration. Accuracy. So suppose we repeat this hashing scheme log n times in parallel. And just like as we saw for L1 heavy hitters, we get an estimate for each of those repetitions. And we take the median across the log n repetitions. OK? Then what you can show is that every frequency, fj, is simultaneously approximated up to an additive error, which is square root f2 over b. OK, so let me say where this is coming from. First of all, since you're repeating this log n times, the frequency is going to be approximated up to this additive error with very high probability, 1 minus 1 over n. And so you can union bound over all the items to get a guarantee for every item. Now, why is this the additive error that you get for a frequency? Well, b is the number of hash buckets. OK? And in expectation, I have f2 over b amount of, the fraction of f2 that goes into any particular bucket is f2 over b. OK? So the sum of squares of the other items that collide with I is about f2 over b in expectation. And now, if I look at what this term is, I'm not taking expectations anymore, but I'm actually looking at what it is. It's a random sign sum of everything else that goes into the same bucket. If I take the inner product of a vector and a random sign vector, it concentrates at the Euclidean norm of that fixed vector. The Euclidean norm is exactly, the squared Euclidean norm is exactly f2 over b, the sum of squares of items that go to that bucket. Okay? So that's why this thing concentrates to the square root of that value. So it's the square root of f2 over b. Yeah? So you see if I set b to be some function of epsilon and phi, this will be like epsilon root f2. If I can approximate everyone up to epsilon root f2, then I can figure out this heavy hitters problem, right? Because I just check, is it large or small? What is the space complexity? Again, for this part of the talk, think of epsilon and phi as being constant. It's log squared n bits of space. Why? Well, it's actually, I have B buckets. Each bucket I'm maintaining a counter, this signed count. So that's B times log n. And I have log n repetitions. So it's B log squared n. And B is a constant. I set B to be a function of epsilon and phi. So it's log squared n bits. Yeah? OK. Good. So this is the previous known way of finding L2 heavy hitters in the data stream. It achieves log squared n bits of space. And it's known if the stream is allowed to have deletions to items in addition to insertions, then it's actually optimal. OK? And just note that this data structure is very easy to maintain with deletions, right? If I say delete one copy of item 2, then instead of adding the sign to the counter, I just subtract the sign from the counter. OK. And so it's optimal. But what about insertion-only streams? I just see updates to items. So this was a model originally introduced by Almaden, Matthias, and Segedi, which captures a lot of applications, internet search logs, network traffic, databases, scientific data, etc. What is the bound for insertion streams? So the lower bound is log n bits. Right? I need to specify the identity of a heavy hitter. If epsilon and phi are constant, they're at most a constant number of heavy hitters. Log n bits is the only known lower bound. But there's a log squared n bit upper bound. All right, so what is the answer here? So we give an algorithm which gets log n bits of space. Very close to this log n bit lower bound. And actually recently, I'll touch on at the end of the talk, is we can get rid of the log n and we get log n bits of space. So we improve CountSketch. And the same technique gives a number of other results. So suppose you want to estimate f2, the sum of squares of frequencies, at all times in a stream. OK, so at every single point in the stream, maybe this is getting back to your question. Every single point in the stream, I want to know the value f2 up to a constant factor. Then we can do this with log n bits of space. And the reason this is interesting is because it's known to estimate f2 with error probability delta at any given time. It's known that the space complexity is theta log n log 1 over delta. OK? And so the natural thing here to do would be to set delta to be 1 over n, or 1 over poly n, the length of the stream. And then you're guaranteed to be correct at every point, but you're using log squared n bits of space. Whereas we're getting log n log n. OK? This improves an algorithm of Yi et al. And others, which they got some savings, but they always required log squared n bits of space. So they only got savings when m was sufficiently larger than poly n. There's also a natural problem. Suppose I just want to compute the maximum frequency up to some additive error. OK? So this can be done with log n bits of space, whereas the previous thing would be log squared n bits of space. OK, so in this talk, I'll focus on the heavy hitters algorithm. OK? So now I'm going to try to give an overview of this proof and the algorithm. This is the problem. We're going to output all those items I whose squared frequency is at least, say, phi times f2. How many items can there be? I mean, how many items occur at least 10% of the f2 value? There can be at most order 1 over phi such items, which is a constant for us. So suppose at the beginning of the algorithm, I just hash the items into a large enough constant number of buckets. Then all these heavy items will go to a separate bucket. They'll be isolated with good probability. That's just what this says. All those items get perfectly hashed with 1 over phi squared buckets. And so the problem just immediately reduces to the following. we just have a single heavy hitter I star, and we want to find it. Okay? So we have some heavy hitter, Fi star, whose frequency is at least square root phi of 2. Okay. So let me start with some intuition. The intuition is, suppose that single heavy hitter I star has frequency at least root n log n, and all the other items have frequency 0 or 1. Okay, so this is a very unrealistic assumption, but just to give you intuition for the algorithm, note that if all the other frequencies are 0 or 1, the F2 value here is n on these items. But this guy, to be a heavy hitter, only needs to have frequency at least root n. But I'm saying his frequency is even larger. It's root n log n. Okay, so that's also unrealistic. It's an even stronger guarantee than L2, but this is for intuition. Okay. And for the moment, let's also ignore the accounting for storing random bits. Okay, so let's ignore the space complexity we need for random hash functions. So like in CountSketch, we're going to start off by assigning each coordinate, each item, I, a random sign, sigma I. Same way as in CountSketch. And we're going to do something like CountSketch. So let's randomly partition the items into 2 buckets, just 2. And we're going to maintain a random sign sum in each bucket. Okay, just like in CountSketch. All right, so C1, our hash function is h. This is the counter for all the items which hash to the first bucket. C1 is the sum over items I that hash to the first bucket of their sign sigma I times their frequency. And C2 is the same thing for the second bucket. Okay? So my question is, let's suppose that the single heavy hitter I star we're trying to find lands in the first hash bucket. My question is, what do the values C1 and C2 look like as the stream evolves? Okay? So here I've drawn an unbiased random walk. At each step, I go up with probably 1/2. Each step, I go down with probably 1/2. Up by 1, down by 1. So I claim these counters basically look like random walks, unbiased random walks. So why is that? So let's look at this first counter, C1. We said I star, this heavy hitter, goes to that bucket. Let's take out its contribution. Let's write it over here. Sigma I star times Fi star, plus all the remaining items that go to that same first bucket, their contribution to the sum. And the second counter, let's just leave it the same way it was before. Okay? Then the claim is that if I look at the first counter and I subtract off the contribution from the heavy hitter, sigma I star Fi star, I'm just left with this. Or if I look at C2, these both evolve as unbiased random walks as I go through the stream. Now why is that? Well, we said all the frequencies of other items were 0 or 1. So they're only going to appear once, at most once. We said we're not accounting for random bits right now, so all the signs are independent. So I see an update to an item, and it tells me to go up, increment with probably 1/2, or to go down with probably 1/2. It's an unbiased random walk. Okay. What do we know about random walks? So the following is Levy's theorem. It's a standard theorem on random walks, which basically bounds their deviation from the origin at all times. Okay, so what it says is there's a positive constant c, so that with some constant probability, say 90%, at all times, these random walks are bounded in magnitude by c times root n. Okay, so I'm never going to deviate, from the origin by more than c times root n at any time in the stream. Okay? And this is already an interesting statement. I mean, well, it's a standard statement, but it's sort of interesting in the sense that it's avoiding sort of a natural union bound, right? It's saying that you don't have to say at this time, with good probability I don't deviate too much, and then take a union bound over all times. This is a statement that simultaneously captures what's happening at all times. Okay, so let's look at what happens here. So suppose this event holds, that these are bounded at all times. Well, this heavy item I star, at some point we see at least 2 c root n updates to it. Okay, I mean it has frequency root n log n. At some point we're going to see at least 2 c root n updates. And this heavy item is going to be in one of these 2 buckets. And no matter what its sign is, it's going to make the counter C1 or C2 larger than c root n, just by the triangle inequality, right? It's 2 c root n. These things are bounded by c root n. At some point, one of the counters in magnitude is larger than c root n. But then we know that bucket contains I star. So we've learned one bit of information, in a sense, right? Because we've hashed the items randomly into 2 buckets. And now we know that I star is in this bucket, which says the hash of I star is 1. That gives us intuitively one bit of information about I star. Yeah?
But so far you spent log n bits to storage to learn.
So far what?
To learn this bit of information, you spent log n bits of storage to learn.
That's right, yeah. We have 2 counters, right? And each one is represented with log n bits, yeah.
When you say can't repeat log n times in parallel, you mean efficiently?
Yeah, that's what I mean. So suppose we were to repeat log n times in parallel, what would we get? We would get CountSketch, right? I mean, more or less. And that would be log squared n bits. So instead what we're going to do is repeat things sequentially. Okay, so the idea is we wait until one of these counter magnitudes exceeds c root n. If it's the first counter, then we know h of I star equals 1. Otherwise, it's the second counter, and h of I star equals 2. This gives us one bit of information about I star. And now we just start over. Okay? So what we're going to do is initialize 2 new counters to 0 and perform the procedure again. Okay? Note that the space doesn't get multiplied, right? Like we're doing it sequentially, so we're always using order log n bits of space. We threw away our old space. We repeat this procedure again, and assuming the frequency fi star is at least root n log n, you will have at least a large number of repetitions, say at least 10 log n, and you will be correct in a good fraction of these repetitions. Okay? Meaning that you identified the bucket that contains I star. And then by turn-off bounds, note that these are independent. By turn-off bounds, there's only going to be a single value of I star. If I look at all the items in the universe, there's only going to be a single item which agrees with a 2/3 fraction of these larger. Right? So we're saying this bucket is larger, or now this bucket is larger, now this bucket is larger. There's only going to be a single item which agrees with a 2/3 fraction of those, and that will be I star. Everyone else is going to, in expectation, agree with half of those. Okay, we have log n repetitions. We can union bound over all items. So this is the idea behind repeating sequentially. Okay, so that's a nice intuitive algorithm, but there are some problems. Namely, these assumptions are not realistic, right? So we don't have all the remaining frequencies being 0 or 1. And even if they were 0 or 1, this large frequency would only need to be at least root n to be a L2 heavy hitter, as opposed to root n log n. So we want to remove both of these assumptions, and we will do that using the theory of Gaussian processes. So let me say what those are. So a Gaussian process is a collection of random variables indexed by this set capital T. X sub little t is one of those random variables. And what we have is, for every finite linear combination of the random variables, it's Gaussian. Okay, for us, this index set T, capital T, is finite. We have a finite number of random variables. And this is just saying that every linear combination of these random variables is Gaussian. Right? In particular, the individual random variables are Gaussian. Okay, that's all that definition is. For us, we can assume that these random variables all have mean 0. That's all we'll need.
I am looking at the statement and I'm thinking martingales. So
Martingales.
martingales would give you the loops inequality will give you the separation without the log n.
No, you need to learn log n bits in that process, right? So
I'm saying the guarantee of fi star.
yeah, but I mean the reason fi star was that large is because I needed to learn log n bits about it. So right, so yeah, martingales is sort of a different. I mean, it's not. It's like a different concept, right? I mean, that's like it's not a concentration issue really. It's well, let me just explain. Collection of random variables, any linear combination is Gaussian, mean 0. You can show the process is entirely determined by the covariances, the expectation of xs times xt. Okay? And this is related to the fact that a Gaussian distribution is determined by its mean and covariance. Okay? You can define a distance function on these indices. So the distance between s and t is the square root of the expectation of xs minus xt squared. Okay? So, I take the Gaussian, xs minus xt. I take its expected squared magnitude in the square root. This is a metric on t. It's actually a pseudometric because this could be 0 when s does not equal t, but it satisfies triangle inequality. Let's just call it a metric. Okay, so why do we care? What is the connection to data streams? Suppose we were to replace the sign sigma I with standard normal random variables, g of I. And consider a generic counter C, meaning a counter at time t is the sum over all items I of the frequency f sub I at time t times the Gaussian g of I associated with the item. Okay, so it's like a random sign sum, except I've replaced the signs with Gaussians. Okay, and I'm looking at the counter as the stream evolves. So at time t, fit is the frequency of item I after t insertions. Okay, so this thing, there's a C1, a C2, C to end of the stream. Okay. So the main point is that C of t is a Gaussian process. If I look at the collection C of t at all times, it's a Gaussian process. Why? Because I take any linear combination of these things, and I just match up the Gaussians. Okay, so these Gaussians are independent. I add up the linear combination. I'll get a sum of Gaussians times a scalar. Each Gaussian times a scalar. Sum of independent Gaussians is itself Gaussian, so this is a Gaussian process. Yeah? OK, so why are we doing all of this? So we're going to use a powerful theorem for Gaussian processes called the chaining inequality, which says the following. So let xt, this collection, be a Gaussian process. Now we can define a nested sequence of subsets of these indices however we like, subject to the following conditions. So this sequence is inside of this set of all indices t, and t0 is inside of t1, inside of t2, etc. The size of the first set is 1. The size of the I set is at most 2 to the 2 to the I. So you define these sets however you want, subsets of indices. And the chaining inequality tells you a bound on the expected maximum value of x sub t for any of your random variables. Okay, so I maximize over all my random variables in my index set. I look at its expected the maximum. The expectation of the maximum is up to a constant factor, the maximum over all these indices t of this weighted sum. Okay, so this weighted sum is the sum over all non-negative integers I of 2 to the I over 2 times the distance function. Distance from t to set capital T sub I. Yeah?
If you didn't have the index sets, this is due to not being an inequality. It's not a concentration problem. It's a probability that you're within the band around the expectation. That's the expectation of the max. Is
Yeah.
So
Okay.
without the index sets,
Okay.
this is due to
So I'm not sure if it would give. Okay. So you'll see how I'll use these. Yeah. Okay. So basically I can. Okay. So what is this for us? Xt is like a counter at time t. And then what I'm doing is I'm looking at the expected maximum value of that counter at any time in the stream. And I'm upper bounding it by some quantity, which is a function of this distance function that I'm free to define. So, okay, the distance from an index t to a set is the usual thing, right? It's the minimum over all items in the set of the distance of t to that item. Yeah. And so this is the upper bound, and I get to choose these sets ti however I like. So how can we apply this to our Gaussian process, our counter C of t, which is the sum of the frequencies at time t scaled by their Gaussians? So what we're going to do is we're going to define this nested sequence of subsets based on where the f2 value of the stream changes. Okay, so recall f2 is the sum of squares of all the frequencies. f2 at time t is that quantity after seeing t updates. And the intuition, which I'll show on the next slide, is the ti is going to be a recursive partitioning of the stream based on where f2 of t changes. Okay? So let me show you on the next slide to make it clear. Okay. So here's our stream of items. At the end, there's an f2 of m, right? I have m stream updates, f2 of m. Let a sub t be the first point in the stream, that update, for which the f2 value at time t is at least f2 of m over 2. Okay, the first time for which it becomes at least half of the overall f2 value. We let our base set, t sub 0, be that index t. Okay? And now ti is defined as follows. So this was t0. We're going to partition the stream into 2 to the I pieces. Right? We said ti, the chaining inequality allows ti to be as large as 2 to the I. Let's fully exploit that. We're going to break it up. So ti is going to be a set of times in the stream, t1, t2, t to the I, such that tj is the first point in the stream for which the f2 value at time tj is at least the f2 value at the end of the stream times j over 2 to the I. Okay, so we're j of the way there out of 2 to the I breakpoints in the stream. Yeah.
Do you remember the f2 value?
No, this is analysis. Yeah, this is all analysis. This is not algorithmic. Okay, so let's just verify these conditions. So t0 has size 1, and this is indeed a nested sequence of subsets, right? Because t1 is inside of t2, blah, blah. They're the right size. Okay, so let's apply this chaining inequality and see what we get. Okay, so on top here, I've just rewritten the chaining inequality. Okay, it's the same thing. So to apply this chaining inequality, I need to compute this distance function. Okay, I've told you what the sets are now. But what is this distance function? Okay, the distance from index t to a set ti, we said it's the minimum. Yeah, so it's the minimum over all items tj in that set ti of the distance from t to tj. Well, what is the distance from t to tj? Well, recall, it's the square root of the expected value of ct minus ctj squared. Yeah, sorry, this min should actually be outside of the parentheses, but it's the same thing. Okay. Well, what did we do? So what is CT minus CTJ? This is the counter at time t at the counter at time tj. What's the difference of those two things? I mean, it corresponds to the updates that occurred between time tj and t. Right? And what did we do? We evenly partitioned the stream based around the f2 value. Yeah. So this expected distance squared, I mean, expected value of ct minus cj squared is at most f2 over 2 to the 2 to the I, because we split the stream based on f2. So this quantity, this distance, is the square root of f2 over 2 to the 2 to the I. You can just calculate this based on our partitioning. OK. But now we can just plug this in to this chaining inequality. And what do we get? We get the expected maximum of our counter at any time in the stream is up to a constant factor, the maximum of this weighted sum. Well, what is the weighted sum for a given t? It's the sum over all integers I of 2 to the I over 2, this scale factor, times this distance, which is square root of f2 over 2 to the 2 to the I. OK, that converges super quickly, right? So that's just order square root of f2. OK, so this is interesting for a reason. This is actually the same behavior as for random walks, right? So this is saying the maximum at any time t, if I had a stream of length n, with these 0, 1 frequencies, then this theorem from random walk says, oh, the deviation is going to be at most root n. This is the same statement, except it's much more general. OK, so it has the same behavior as for random walks. And so let's just see. So we wanted to remove these two assumptions, that all the frequencies that are not heavy are 0, 1, and the heavy frequency is at least root n log n. This Gaussian process just immediately removes the restriction that all these remaining frequencies are 0 or 1. Right? I mean, it gives the same bound as for random walks. The random walk bound of c root n we needed now holds just for arbitrary frequencies. We made no assumptions on the frequencies in that Gaussian process argument. OK, so we still need the frequency to be at least root f2 log n to learn log n bits about this heavy hitter. We haven't removed that assumption yet. OK, but this, yeah, learning 1 bit at a time of this heavy frequency, this now works for arbitrary frequencies, not necessarily 0, 1, using this Gaussian process bound. So how do we remove this last restriction? So here, so you can assume that, this is assuming fi star is at least root n log n, which is really heavy. You can assume it's at least root n times any sufficiently large constant just by, at the beginning of the stream, hashing into a large number of buckets. And then the expected f2 value in a bucket is going to be f2 divided by the number of buckets. You can afford constant factor blowup. So we can assume it's a large constant times root f2, but we can't assume it's at least root f2 times log n. OK, so we have this thing that we call amplification, this technique, which is going to effectively make this, this heavy guy that's frequency at least a constant times root f2, we're going to make him frequency at least log n, polylog n times root f2. And then we can apply the previous analysis. So if we have some technique for boosting its frequency with respect to f2, then we can apply the previous argument. The way we do that is we create log n pairs of streams from the input stream. OK, so we have our input stream. And we split it into two pieces, a left piece and a right piece. And we do it at random based on the items. OK, so we look at the n items, and for each item I say, oh, all of its updates are going to go to the left stream, or all of its updates are going to go to the right stream. So I partition the stream into two pieces. And I do that independently log n times. OK, so just like, in case that wasn't clear, formulaically, it's, for each j between 1 and log n, I choose a random hash function, h superscript j, from the items to 0 or 1. And the left stream in the jth repetition is the original stream restricted to updates to items I, which the jth hash function evaluates to 0. And the right stream is the remaining part of the input stream. OK. And similarly to everything we've been talking about, I maintain two counters, one for the left stream and one for the right stream. OK, so it's just the inner product of the frequencies that go to that bucket with this Gaussian vector. So the main point here is the following, which uses the chaining inequality again. So suppose I star goes to this bucket. Then what's going to happen is by the chaining inequality, or think of this random walk bound in the restricted case, these two counters are going to be at most root f2. And they're going to stay at most root f2 forever. Because the chaining inequality says the maximum these counters will ever be is at most root f2. On the other hand, after I see enough updates to this heavy hitter, one of these counters is going to be larger than root f2. Because if I see 10 or 2 root f2 updates to I star, then this counter is going to be larger than root f2 by triangle inequality. So the counter which has I star is going to be larger. And it's going to be larger forever, because the chaining inequality says the maximum at all times is at most root f2. Yeah, so the larger counter stays larger forever. And so the idea is we run the algorithm only on the items which agree with a 9/10 fraction of the larger counters. For simplicity, let's just suppose, so I have these log n pairs, right? And one of the two counters is larger in each of those log n pairs. Okay? And most of the time, it's, in fact, assume for simplicity, all the time, the larger counter is the one which has the heavy hitter. Okay? Then every other item, the probability it agrees with the larger counter is going to be 1/2. And we have log n repetitions. So if we only run the algorithm on the items which agree, at least a 9/10 fraction of the time, we're going to filter out 1 over polylog n of the items. Okay, so what that does is if we only run it on the items that agree with these larger counts, then the expected f2 value of those items is now f2 over polylog n. Right, because we have log n repetitions, a 1 over log n fraction are going to be left in the stream with the heavy hitter. So their f2 value goes down, but the heavy hitter is still there. So it effectively is now heavier. Because the f2 of everything else is smaller, but it stayed the same. So now it's polylog n heavy. Okay, so that's the idea here. Now, there's some details here that I didn't explain. Basically, these counters, like the larger of the two counters does change in the beginning of the stream. It changes a lot. But at some point, it stops changing, okay, because of the chaining inequality. And after I see enough updates, none of these counters change. And so if I'm always learning this one bit of the heavy hitter at a time, if I just look at a suffix of the stream, then it will be on counters that are not changing. So there is some garbage at the beginning of the stream. But after I see enough updates, this process works. So it was a bit fast, but basically the idea is to restrict to a subset of items, blow up the space by a log n, and this effectively makes I star heavier. Now it's, it has this guarantee we needed earlier of being log n times the f2 value. OK, so let me just make a few remarks on derandomization. We don't actually have an infinitely long random tape. We need to derandomize a few things. One is the Gaussian process. Right? I mean, we have this counter where we're multiplying all the frequencies by Gaussians. That's a lot of randomness. Another thing is we have these hash functions that are used to sequentially learn bits about the heavy hitter. Naively, like we're learning log n bits. Each time we're choosing a hash function with log n bits. That's log squared n bits. We need to derandomize that. The more interesting thing is derandomizing the Gaussian process. And here we use a derandomized Johnson-Lindenstrauss theorem. So I don't know if you guys know, everyone knows Johnson-Lindenstrauss or no? Okay, no? Okay, so let me say what it is. So if I have a big vector and I multiply it by a random matrix which is very wide and fat, I multiply it on the left. Sorry for you guys, yeah. Then like I squash this vector down to something very small, and the Euclidean norm is preserved. Okay, so Johnson-Lindenstrauss says I can take a big vector, randomly project it to a small vector, and the Euclidean norm is preserved. This is a big matrix to do this projection, a big random matrix. But what Kane, Mecca, and Nelson showed is that this matrix can be specified using only log n, log n bits of space. Okay, so you can get a very concise representation. And basically what we do is we have all these counters. Right? We have counters of the form like Gaussian I times Fi, you know, I equals 1 to n. This is at some particular time in the stream. And what we do is we first squash this frequency vector, which is n-dimensional, down to a log n-dimensional vector by applying this Johnson-Lindenstrauss transform. And now it's only log n-dimensional, and now we can afford to choose log n independent Gaussians for each of the coordinates, because now it's very small. We also can't use Gaussians because they're infinite representation. This whole analysis actually works if you use sign random variables. So really, you just have to maintain log n sign random variables, which you can do in log n bits of space. And the point is, why is it OK that all these frequencies, the vector got squashed? Why do I still have all the same behavior in the algorithm? And the thing is, there's this thing called Slepian's lemma, which says that if I have a Gaussian process, it's entirely determined by its covariances. And what's happening here? Well, when I do Johnson-Lindenstrauss, and I look at, OK, yeah, I'm out of time. I do Johnson-Lindenstrauss, I look at a covariance. This is just a Euclidean distance between 2 points in the stream. And the Johnson-Lindenstrauss lemma is preserving all Euclidean distances. There are n squared pairs of these at points in the stream. So all the covariances are preserved up to a constant factor, which means by Slepian's lemma that actually the process is the same. This chaining inequality still holds. Yeah, so I'm out of time. The second thing can be derandomized using Nissan's pseudorandom generator in a similar way that, if you've seen it, that Piotr Indyk used in some of his work. We have an optimal algorithm now which gets log n bits instead of log n. This is in follow-up work. This Braverman, Chestnut, Ivkin, Nelson, Wang, and myself. Now this log n factor is coming from a few places. This amplification technique, that was probably the most confusing part of the talk. You can actually improve that using a tree-based scheme and some observations that, about the heavy hitter becoming heavier as you walk down the tree. I won't get into it. The derandomization was also causing us this log n. You can show that actually you can use 6-wise independence to derandomize the whole Gaussian process. And so let me just conclude. So we beat CountSketch for finding L2 heavy hitters in a data stream. Using this follow-up work, we get log n bits of space instead of log squared n bits of space. As I mentioned, it has other applications to estimating F2 at all points in a stream. And there's a direct corollary of just finding the maximum frequency, since we're finding all the heavy hitters. Open questions, again, just like for the first talk, is this a significant improvement in practice over CountSketch? And another interesting question is, to me, is that so Gaussian processes seem to be a key idea here for getting this to all work. And can it be used for other problems in insertion-only streams to get better bounds? So that's all. Thanks.